Share. Okay. Yeah, people. Okay, let's do this exercise. So given a set of a relation R which has 4 tables, 4 attributes, A, B, C, D. Let's compute its, and the set of function dependencies, A determines B, B determines C, BC determines D, and AD determines B. Yeah. Check if AD is a key of R. How do I do this? How do I determine whether AD is a key for R? I compute the closure. So I compute the closure of AD. Yeah. So basically the set of attributes that functionally depend on AD. I have A, I have D from trivial functional dependencies. What can I deduce from the functional dependencies F? B and C. So basically AD determines A, D, B, and C. So is it a key? We can't answer this question. We can only say that it is a super key. Why super key? Because it determines all the attributes in the table. So is it a key? Now, to answer this question, I have to compute the closure of A and the closure of D, and make sure that neither of them is a super key. So the closure of A is A, and from this I get B because A determines B, and from B I get C because A determines, B determines C, and I have BC determines D, so I get that I have D as well. Right? So A determines A, and I have B from A determines B, and then C from B determines C, and I have BC determines D, so I get D. Okay. So the question now is D a key? No, it's not. Yeah. Why? Because I have a subset of it that is also a key. It determines all the attributes in the table. Exactly. So AD is not a key. Okay. I can find only one subset. This is sufficient. So I don't have to make sure that D is also a key. In fact, it's not a key. D determines only itself. Yeah, but A is a super key as well, and since it's one attribute, that it is minimal. Yeah, so this is really what I would pick as a key for this table. Yeah, because it determines all other attributes. Okay. How do I check if B determines CD holds? What do I need to do? I need to compute the closure of B, yeah, and see if C and D are both there. So B plus the closure of B is the attribute B, and from B determines C, I get C, and from BC determines D, I get D. Okay. So is B a key or a super key? No, it's not, right? Because it doesn't determine it, so it doesn't determine all the attributes in the table. Okay. But I have, right, does B determine CD? Yes, it determines CD. Yes. Why? Because C and D are both in the set of the closure of B. So B determines C. Okay. Clear? Questions? So minimal cover of functional dependencies. So this is the last thing we're gonna talk about today. And then I'll summarize what we've done and why is this related to identifying whether a table is poorly designed. And then we'll talk about normalization in the next topic. Okay. So minimal cover of functional dependencies. What does this mean? You're given a set of functional dependencies. So let's say like the previous example here, F, and you want to get the minimum cover of them. Meaning what? Meaning you want to get rid of redundant functional dependencies. You want to get the set of the minimum number of functional dependencies and in the simplest form possible. Yeah, that's what I mean by a minimal cover functional dependencies. So a minimal cover or basis for a set of functional dependencies is a set that satisfies the following conditions. It's a set E that is equivalent to F. So it has to be equivalent to F. So exactly, you can deduce the same set of functional dependencies from E as from F. Yeah. However, E has a single attribute on the right-hand side. So it's characterized by having a single attribute on the right-hand side. So you can't have a functional dependency like this. For instance, B determines CD. This is not Allah. Yeah, this is not part of it wouldn't be part of a minimal cover, this functional dependency. So it has to have a single attribute on the right-hand side. We can also remove any attribute from the left-hand side and it remains equivalent to F. So basically, if I remove, for instance, B from here or C from here and check, is it still equivalent to F or not, right? If it's not, then it can be part of the minimal cover. And we cannot remove any dependency from E and it remains equivalent to F. Okay. We'll do an example on this, but let's start by discussing what does it mean to have two set of functional dependencies be equivalent. It means the following. It means that all functional dependencies in E can be inferred from F and vice versa. So all functional dependencies in F can be inferred from E. So how do I test if two sets of functional dependencies are equivalent? I check for each alpha determines beta and E, check if it holds given F. And for every alpha determines beta in F, check if it holds given E. How do I do this? I compute the closure of alpha under E or under F. Yeah? Let's see an example or an exercise. So we have a relation R and two sets of functional dependencies. F, which contains 4 functional dependencies, and E, which contains 2 functional dependencies. And I want to prove that these are equivalent, or I want to make sure that these two are equivalent. How do I do this? I have to check if every functional dependency here holds given the functional dependencies here. The easiest way to do this is to do closure. So I'm going to compute closure of A under E. And see if it gives me A determines C. So what is a closure of A under E? So I use the functional dependencies in E to get the closure of A. It's A, and then you have C, and you have G, because A determines C and G. Anything else? No, right? So the question now is, given this, does A determine C holds under E? And the answer, of course, is yes, because C is in the closure of A plus. Let's do AC. So we'll do the second one. Yeah. So AC. What is the closure of AC? Under E. So using the function dependencies in E, because we want to determine that this is equivalent to that. So AC plus is A and C. And given that A, you have also G, so you get A, C, and G, like the previous one, like A, right? It's A, C, and G. So does AC determine G? Yes, AC determines G holds under. Sorry for my handwriting. Yeah, it's not easy to do this with on the laptop. Okay, what about H determines AG? So I'll do the compute the closure of H under E. Okay. Okay, for those people who are late, what are we doing again? We're doing something called determining whether two sets of functional dependencies are equivalent. How do I do this? So given this relation and a set of functional dependencies F and a set of functional dependencies E, how do I determine whether F and E are equivalent? Meaning what? Meaning I can deduce or infer every functional dependency in F using E and vice versa. So I'm going to compute the closure of every functional dependency or of every attribute in a functional dependency in F under E and see whether the functional dependency holds and vice versa. Okay, how do I write in text? What do you mean by that, Georgie? I don't know what that means. I will look into that the next time, for the next time. Yeah, but for now, for the sake of time, let's just go with this. I hope you can read, still read, okay? Okay. So H plus, what is H, the closure of H under E? So I look at the functional dependencies that depend on H. I have H determines A, H determines I, H determines, that's it. And then I have A determines C and G. So I get C and I get G. Okay. So does H determine AG? Yes, H determines AG under, because closure of H under E has both attributes A and G. Yes. Okay. Questions? Okay. Final one is H determines I. Yes, H determines I because, as you see, I is in the closure of H. So H determines I holds under. Okay. So I've shown that all the functional dependencies in F can be deduced from E, yeah, using the closure. Now I need to do the opposite direction. So I need to check if everything in E can be deduced using F. So let's start with A, closure of A under F. What is the closure of A under F? It's A, C, G. That's it, right? Okay. Correct? Yes. Okay. So does A determine CG? Yes, A determines CG under F. So it holds. So this one holds. Now let's try H determines AI. So I have to compute the closure of H under F. And that's using the functional dependencies in F. So what does it have? H. Okay. What else? I have H determines A, so I get A. I have H determines G, so I get G. I have A determines C, so I get C. I have AC determines G, so I get A like G again, and I have I. Why? Because H determines I. So I have all the attributes basically, except for B. Yeah. Okay, so this H is not a key of the stable type. Now, does H determine AI? Yes, H determines AI. So I can deduce all the functional dependencies in E using F. It holds. This one holds. So now I can determine all these functional dependencies using F, and I can determine all of these functional dependencies or deduce them, infer them using E. So this tells me what? This tells me that both set of functional dependencies are equivalent. Yeah. So this is what we've done. This is the solution that we've gone through in detail together. Any questions? Okay. So now we go back to the minimal cover, which is the last topic we're going to talk about. So we're a bit ahead of time in our schedule. Usually this takes 2 lectures, but since it's less interactive, not everybody is here, so it's taking faster time. So we might have to, we may maybe finish a bit earlier this semester than anticipated. Yeah, we'll see how things go. So given a set of functional dependencies F, we want to compute the minimal cover E. Why? Because this will be used in the normalization approach later on in the next set of slides or the next topic. Okay, so I have originally a set of functional dependencies F which hold on this table. I want to compute the minimal cover. So what do? I first replace every functional dependency that have more than one attribute on the right-hand side with a set of functional dependencies that have a single attribute on one side using the decomposition rule. So I apply the decomposition rule to get, to single attribute on the right-hand side. And now for every functional dependency that I have left, I look at if X, right? So let's say X determines A. If X consists of multiple attributes, I try to remove some attributes and see if I can still get a set of equivalent functional dependencies. Yeah, so I try to reduce the size of the functional dependencies by removing attributes from the left-hand side. Yeah, this is not always successful, but I have to try. So it's a trial and error. Okay, and now finally, I look at all the functional dependencies that I have and remove any redundant ones, any ones that I can infer from other functional dependencies. That's what gives you the minimal cover. So let's see an exercise or an example. And then after that, we're gonna do. I'm gonna put this in context, yes, because we've talked a lot about a lot of topics today. So I want to relate this to our initial motivation. So we have a table with just 3 attributes only, and a set of functional dependencies F. A determines BC, B determines C, A determines B, and AB determines C. Okay. So we want to find the minimal cover of F. Let's start by the first step is to break down the attributes on the right-hand side into single attributes. Yeah. So I know that A determines BC. From this, I get that, right, F dash. So this is an equivalent set to F by breaking down this A determines BC into A determines B, A determines C, and I have, that's it, right? So this is the only one which has 2 attributes on the right-hand side. B determines C, A determines B, and then AB determines C. Okay, so what did I do? I used the decomposition rule to break down this A determines BC into A determines B and A determines C. Okay, why? Because this is the minimal cover should have always only a single attribute on the right-hand side. What is next is to try to get rid of attributes on the left-hand side. So try to see if I remove B, for instance, can I still get this functional dependency AB determines C? Yeah. So let's try to do a functional dependency, and that's again by trial and error. So I'm looking at only the only functional dependency which has 2 attributes on the left-hand side is this AB determines C. So I'm going to try to see if I remove B, would I still have the equivalent set of functional dependencies? So A determines B, A determines C, B determines C, I have A determine B, and then I replace AB determines C with A determines C. And let's see if this is equivalent. So how do I make sure that this is equivalent? I have to be able to reduce all of these from these and all of these from that. Obviously, all of the other ones, so A determines B, I can reduce it from F dash because it's part of the f dash, f double dash, A determines C, so I can deduce it from here and here. So basically only I have to check whether A, B determines C can be deduced from this. Yeah, this is the only thing that I need to do. The rest of the things are already in the other functional dependency, so I don't really have to do anything. So let's see if AB determines C under F double dash. So how do I do this? I compute the closure of AB under F double dash. This one, reduced one that I create. Okay, that's equal to A and B. And what else? I have from A determines B, so I don't get anything. A determines C, I get C. And then that's it, right? So this is what is the closure of AB under F double dash. So does AB determine C? Yes, AB determines C under F double dash. So yes, this holds. So basically I can replace this with A determines C. Okay, now I have some redundancy that I would like to get rid of to get this to a minimal cover. Now everything on the right-hand side is single attribute. Everything possible on the left-hand side, I managed to reduce to single attribute. This is not always possible or not always the case, but in our example, it worked. Now I need to get rid of redundant functional dependencies. So I have AC twice, I remove one. I have AB twice, I would remove one. And now I have AB, AC, and BC. There's a functional dependency here that I don't need. I can infer from the other functional dependencies. Any thoughts? I have AB determines, A determines B, B determines C, and A determines C. I can take A determines C out. Why? Because I know from transitivity that A determines B and B determines C implies that A determines C. So I don't really need this functional dependency using transitivity. Yeah. So basically using transitivity law, I know that, right, I can infer this from these two functional dependencies. So I get the minimal cover of this set of functional dependencies. E is equal to AB and B determines C. Okay. So that's really good. I'll go through the solution again on the slide so that you can see it clearly in case you got lost with my annotation. So I initialized right E to all the functional dependencies in F. That's the first step. And then broke this guy down into two functional dependencies. This is one and this is one, right? Using the composition rule. And then tried to get rid of one of the attributes on the left-hand side because this one has two attributes. So I can try. So I check basically whether I can replace this with AB, AC, BC, AC, and BC. Okay. So I replaced, here I did it differently. I replaced, instead of A determines C, I replaced it with B determines C. Of course, right, it still holds, right? Because if you look at this, right, the closure of AB under this is A, B, and C, and so AB determines C. So whether you replaced it with A determines C or B determines C, it still holds. Okay, so this is equivalent to this. And now I managed to eliminate the duplicates. So I have A, C twice and BC twice. So I remove these two. And now I have AB and BC and AC. Now from transitivity, I know that AC can be deduced from AB and BC. So I get this to be the minimal cover, right? So this is the minimal cover that I have. I have two only functional dependencies that are very simple. I started with a lot of functional dependencies and long ones, and ended up with this simple set of functional dependencies. Let's do another exercise, and then we put this into context. Okay. Questions for so far? Okay, good. So let's see the following relation. We have a following relation which has A, B, C, D, E, so 5 columns, and a set of functional dependencies given by F. Yeah, find the minimal cover of F. Okay. 1 second. I'll unmute 1 second. Okay, I'm back. All right, so let's compute the minimal cover of F. First of all, I have to look at the right-hand side. Do I have any function dependencies that I can break, meaning contain more than one attribute? Yes, I have BC determines AD. This can be broken into BC determines A and BC determines. So I'm going to write E, then initially as A determines D. That's a simple functional dependency, so I can do anything about it. I have BC determines AD becomes BC determines A. And BC determines D. Okay. What else? I have C determines B. That's simple. I have E determines A. And E determines D. Okay. So this is what I have. Now I try to get rid of, some of the attributes on the right-hand side, on the left-hand side, if I can. So I can try to see if I replace B, C with B, would I get, the same set of function dependencies, yes or no, and do the same thing for B, C determines D. So I try B determines A or C determines A and see what do I get. So let's try this out. So E, candidate, E dash, right, is A determines D. Okay. I'm gonna try B determines A. And leave BC determines D as is. Okay, C determines B. E determines A. And E determines D. Okay. Determines. Okay. Now the question is this equivalent to that? So let's see. Can I deduce BC determines D from this set of functional dependencies? Or sorry, BC determines A from this set of functional dependencies? The answer is no, right? Because if I compute BC, closure of BC, let's see, BC under this E dash. So I have to use the function dependencies in E dash. That gives me B and C. And from BC I get, from B I get A. So actually, yes, it works, right? From B I get A, and from BC I get D. And from C I get B, of course, and from A, that's it, right? So I have this function dependency, set of function dependency. So B, C, A, and D. So does BC determine A? Yes, it determines A. So I can actually break down, get rid of this guy, and replace it with B determines A. It's again trial and error. I could have tried C determines A instead of C, B determines A. Okay. Now I take this and I try to get rid of also here B or C. So let's try to say make it C determines D. So I have E double dash be equal to A determines D. B determines A. I have what else? B determines D or C determines D. It doesn't matter. I can try. I have to try both, right? If one doesn't work, I can try the other one. C determines B, and so on. E determines A, and E determines D. Comma, E determines. Okay. Sorry for the mess. Let's see. So does BC determine D hold under the set of functional dependencies? Let's see. So I compute BC closure under this set of functional dependencies, E double dash. I get B. I get C. What else do I get? I get A. And from A, I get, right, D. That's it. So does BC determines D? The answer is also yes, because right D is in the closure. So I can get rid of this guy. Or I can, sorry, get rid of this guy and replace it with this set of functional dependencies. So A determines D, B determines A, B determines D. C determines B, E determines A, and E determines D. Now the final thing is to see if I can get rid of any functional dependencies. So can I get rid of any functional dependency here? So I have A determines D, B determines A. So I think I don't see anyone so that. But you could do what you could do is you could of course remove some functional dependencies and check whether you can infer them or not, whether you get an equivalent set of functional dependency. To me, I don't see anyone that I can use a transitivity law or something like this to remove. Yeah, so this might be the minimum set of functional dependencies. Correct me if I'm mistaken. Okay, good. So I want you to do this exercise again on your own at home and before the next lecture. Yeah, so you can prepare to do the next lecture. So let me put this into context. We started with something like this. We have B determines A and A determines D. We can infer B determines D. Yes. So do we have this? 1 second. Do we have A, B determines A and A determines D? Yes. So this one correct, Mira, you're right. So this one can be removed. Oops. What is the pen? So Mira is saying B determines D is redundant. Why? Because I have B determines A and A determines D. So I can infer B determines D from it. Yeah. Do I have anything else that I haven't seen? Also E determines D. E determines D. I have E determines A and A determines D. So basically, yes, you're right. So I can remove, you guys are spot on. So I have E determines A and A determines D. So I can get that E determines D. So I end up with A determines D, B determines A, C determines A, and E determines A. Okay, I think this is pretty much it. Correct? Okay, great. Now the last 3 minutes, quickly, let's go back to the beginning of the lecture. So we started with something like this, a table like this, yeah? And we said this table is poorly designed because you have this functional dependency. Major determines minimum credit. So how do I identify whether a table is poorly designed or it's not in a normal form, if you have functional dependencies in the table that do not, in which, such that the left-hand side, so what functionally determines the other attribute, is not a super key. That immediately tells you this table is poorly designed. So here I have major determines credit card, minimum credit, sorry, and major is not a super key. Hence, this is about functional dependency, and I need to normalize the table. How do I get the functional dependencies that hold on a table? I can write a simple SQL statement. Yeah, so look at really every pair of attributes, or every subset of attributes with the other attributes, and check whether they functionally determine the other attribute or not. Yeah, so check whether the values agree or not. So whenever, right, I have major equal to CS, is it, minimum credit equal to 90? This the case. Yeah, so you can write. We have some code snippet on this, or some slides on this, on how to write SQL queries to detect whether functional dependency. Yeah? So you can really run some SQL queries to get you to whether the set of functional dependencies that hold in a table systematically. So you don't have to really do this manually. Once you have this set of functional dependencies, you identify, you want the minimal ones. That's why we're doing the minimal cover. Yeah? So you identify what is the minimal cover, and based on these, you look at whether there is any functional dependency that violates this key issue, right? That the left-hand side is not. I'll stop here, and we'll repeat this again when we talk about normalization. Okay? So I have less than a minute, so I don't think we have enough time for questions. But if you have questions, perhaps we can discuss them on Thursday. Okay? Yes, I will upload it. I think I put it already, but maybe it's not visible. So I'll make it visible, and I will upload, of course, the recording on YouTube and send you the link. Okay? Thank you, guys. Yes, you should start working on the project. I will send an email with what is required, what is the next phase, and when is it? When is it due? Yeah, very soon. But you should start working on the project. Yeah, good luck. Bye bye. Yes, I will. I will. Don't worry, Steph. Okay. Good. Bye, guys.